So I ran a little late today because it was a very busy day, but here nonetheless, and I don't know what I want to talk about because I checked the books that I had upstairs that I had at school, not upstairs, um, yesterday, and I didn't find anything on waveguides that was terribly unique. I have another book here that I can check for some stuff on waveguides, but I don't know how successful I'll be in finding anything that's unique. I should probably pull the mic over. I don't know how successful I'll be in finding stuff that's unique to waveguides, but if it's not that waveguide stuff, I don't know what else can be done. Is there anything that anyone would like me to go over in particular? Because I don't know what I want to cover. I don't know what's left to cover is the biggest problem, I guess. Does anybody have anything they want me to talk about? Like, is there anything from... Okay, let's do this. Is there anything from any of the tutorials, any topics, anything at all that is unclear or that requires further explanation or anything of the sort? I don't know how much unique material I have to cover, which is a bit of a problem, I guess. Yeah, like I don't see anything here that's, new, I guess. Maybe we can... Well, there was like a couple of questions, I guess. But really nothing. I don't know. It's weird. Maybe I should get stuff ready still. Get my tablet ready, because I still haven't gotten my tablet ready. We go over conditions under different types of media. Can you be a little more specific? Because, well, linear isotropic homogeneous is always true, so you don't need... And so that what that means is that that would never change anything in the types of problems you solve, because we always assume linear isotropic homogeneous. Source free implies Ji is 0 and rho v is 0, and loss free implies alpha equals 0. So I don't know. I don't know what to do with that, to be honest. So because those conditions that you've mentioned, we basically considered them for all of basically Maxwell's equations types problems. But basically this entire course, for the most part, is under those conditions, except for special cases where we're trying to prove something, I guess. Or we're trying to analyze a specific result or something, or a specific scenario. The effects of source-free and loss-free on Maxwell's equations. There are no effects that are unique to Maxwell's equations, but they do have implications. I guess that's what I want to say. So maybe we can talk about the implications. If my pen would work, which it's not. Okay. Okay. The pen's not working. Oh no. Why isn't my pen working? Oh, there we go. So let's then start with tutorial 5. So, what do we want to do? Let's look at how the textbook defines. We don't need to look at the textbook because there's nothing in there from the textbook that's useful. What is source free? Let's look at source free. Source free implies ji is equal to 0 and rho v is equal to 0, right? So then what are the implications of this, to answer your question, on Maxwell's equations? So if I have the curl of E, let's just deal with time domain point form. You have that. The curl of H sees a change because then you have J now plus the time derivative of D with respect to T. But this J, let's consider this the generic case where J, let's say we have conduction and convection, but we don't have, well, if we have convection, it doesn't really matter because rho v is still 0. So basically all we're left with here is conduction current if we have 0 impressed and 0 rho v. And so let's write the general equation first. So we have sigma E. That's a weird looking E. Let's write that. Let's include Ji. Let's include rho v u. And then this D. And then we say, but since it's source free and all that other stuff, source free, whatever, these two conditions are gone. If loss free, let's say, so if it's loss free, then this is also 0, right? Because sigma E has to be 0. If there's no loss, then sigma equals 0. If sigma equals 0, you're left with just this term. So if I were to summarize this, well, we still have two other equations. Why don't we talk about those as well? This is not the right order, so to speak. This would be rho v, and this is b equals 0, and this would also be 0. So source free is Ji. Is that a vector? I'll call it a vector. I don't remember if it's a vector or not. And rho v equals 0, and then loss free sigma equals 0. So this is the implications on Maxwell's equations, I guess, of a source free and loss free region. Throat's feeling really dry. I've been talking a lot today, apparently. And yesterday. So what else do we want to talk about? Did I have any other questions here that we can talk about? don't see anything else that we can work on. Is there any type of problem that is more difficult or is worth spending some time on? So with the question about reflected and transmitted waves. Okay, that's a good question. Thanks for the question. Okay, sorry, before I do this question, I just want to, because somebody just asked about charge free. Charge free implies that rho v equals 0, but ji doesn't necessarily have to be 0 and sigma does not have to be 0. So source free implies both ji and rho v are 0. Charge free implies only rho v is 0. Let's talk about, now we can talk about boundary conditions in TEM problems. I don't know why I'm capitalizing this, but I am. So let's imagine we have a boundary. We have a semi-infinite whatever type of region we have. Let's imagine this is x equals 0. This is region 1. This is region 2. You have some incident wave like this. You have some reflected wave that has a very weird looking arrow. I can't draw the same arrow going the other way. Huh. That's good enough for me. And then that's a transmitted wave. So we can say this is EI, for example. Let's call this ER. Let's call this ET. And the question is, how do we find surface current on the boundary? So we know that there will be a surface current here on this thing here. So this is a surface current. Well, it might be a surface current. It might be a surface charge density they ask you to find. Current or charge, depending on what the question's asking for. Now, to solve this question, you have to account for the boundary conditions, right? So let's suppose we wanted to solve for the surface current density, right? So one thing I should probably add to this is that there's an EI there slash HI, because there's a magnetic field that's incident as well, slash HR slash HT. So there's a magnetic field and an electric field propagating, and the boundary condition equation, so recall from boundary conditions, you have, what's the equation for boundary? It's H1 minus H2, right? Minus H2. And this one is cross AN1, 2. And that gives you K, where K is the surface density, surface current density. So this is surface current density. So then how would we use this to solve our problem? If we want to use this to solve our problem, H1, in this case, we would say this is HI minus H. Well, let's assume that this is not a perfect conductor. Even if it was a perfect conductor, it would be the same process. Minus HT, so I don't know why I mentioned that fact, anyhow. Cross AN1, 2 is equal to K. And so if it's a perfect conductor, HT is obviously 0. And so this becomes HI cross AN12. And K is K. Then AN is... So, I mean, the general form is consistent, is the point I'm trying to make here. So if this is what you would do if you're looking for the surface current density, if you're looking for the surface charge density, for whatever reason, you would end up using the other equation, which is d1 minus, is it d2 minus d1 dot an21, whatever the other boundary condition is. I can probably find that somewhere in the book because I can't remember what the exact direction on the unit vector and all that stuff is, but I'm pretty sure it's it's 2 minus 1. Anyhow, that's the process for the surface current on the boundary. And so if it's a perfect conductor, so we can say here if because sometimes they say, oh, imagine region 2 turns into a perfect conductor. If region 2 is perfectly conducting, we have HI minus 0. Well, let's write HT, and then we'll cross it out after. AN12 stays the same. It's still consistent because it's a direction. We don't care about what's in the other region, right? This thing equals 0, so you end up getting HI cross AN12 equals K. And so in this case, AN12 is the unit vector that goes from 1 into 2. And so you would have a unit vector that goes from 1 to 2. And so this is AN12. Now you can't tell what it is just based on this. You would have to be given an equation for E. So imagine E, let's say I, is equal to E naught e to the minus j beta y a x, let's say. Right? So then AN12 would be the direction of propagation, which is AY in this case. And so then you would have this cross product would be HI cross AY, so then you would have X cross pi, which would give you AZ, meaning the current would come out of the page. I hope that helped, because that's basically all I have to say about that, I think. Unless there's parts that are unclear. Does H1 include... No, so if you see here, I changed this to HI. Right? Because the boundary condition is applied for, if you consider the case of boundary conditions... wait, well, that's a good question. No, okay. That's a very good question. H1 should be the total. So that's wrong. That's wrong. What I wrote here is wrong. Because it should be the total contribution, because the field at the boundary, so this should be HI plus HR. Well, let's change the bracket then, because it'll look a little clearer then. It's a very good point that you just brought up. Well, made me think of, at least. Like this. Reflected field is not negligible. I was thinking about this special case, because here's why. If you imagine what's happening at the boundary, what's happening at the boundary is You have the boundary doesn't know what's being reflected and what's being transmitted. The boundary sees two waves, right? So the boundary sees some incident wave, and this thing sees this. So this is H1 and this is H2. And H1 would be HI plus HR. It wouldn't be minus. Well, I'm assuming that the sign is being incorporated in the actual equation itself, because HI might be H naught R e to the minus j beta y, and then HR is going to be H naught. That's not H naught R, that's H naught I. What the hell am I doing? That's not a vector. H naught I, and this would be H naught R e to the positive j beta y, right? So this and the unit vector on this would account for the fact that it's going in the opposite direction. That's what I'm assuming. Yes, you're right that it would end up being minus, actually, but what I'm trying to illustrate here is that it's the total field that I'm comparing in both regions, right? So you have the total field here, and then you would have just the transmitted here. Later on, when you actually write this properly, you will have a minus sign in there somewhere because they are in opposite directions, but maybe not necessarily because of what the amplitude is. But the change in the opposite direction, or the direction of propagation, is seen here. That's what governs the direction of propagation, not this negative sign here. So that's not what gives you propagation direction. Propagation direction is governed by the exponential, which we learned yesterday. Nobody really understands. So yesterday there was a bit of a, which again I was mentioning during the tutorial yesterday, that I really enjoyed teaching in person because I get to see your reactions when I ask you a question and nobody has the answer. So everybody kind of just looked around yesterday when I was asking how to find out what the direction of propagation is, because apparently nobody knew how to do that. And so the direction of propagation is the exponential. So e to the minus j beta y is propagation in the positive y-axis. E to the positive j beta y is propagation in the negative y-axis. So what you're saying about it being minus may or may not be true, but what I'm trying to illustrate here is that it's the total field component. Yes, there was a tutorial yesterday. Did somebody forget to invite him to the tutorial? I was wondering why you weren't there. I would have expected you to be there, but I figured my tutorial wasn't worth your Friday evening. So yeah. There was an announcement in the Facebook or the Ryenge group. So yeah. Oops. It wasn't, I don't know how useful it was. We did a bunch of waveguide stuff, which I will be posting after this tutorial. So, but yeah, it was fun. I haven't taught in a while, I mean, I'm doing these tutorials, I guess, but I haven't sat in a classroom and taught in a while. Well, I don't know if you missed much. We did waveguide stuff. We mainly spent time doing waveguide stuff, which is why I wasn't overly concerned, or not concerned. I don't know if concerned is the right word, but I wasn't overly upset that I missed an hour today because I knew we did an hour, or we did 2 hours, 2.5 hours almost yesterday. So what I'll do is I'll post the notes because they're on my laptop. I'll post the notes whatever after this tutorial. If you have any questions about the tutorial, we can talk about those questions. I don't know, sometime. It's not recorded. No, it's not recorded. Don't be relieved. I don't mean to discomfort you some more, but it's not recorded. I have notes though. There's no recording. It just keeps getting worse. Oh man, that's awful. What I do want to do eventually, and I say this about every course and everything that I teach, is I want to put all of these problems, like in some type of library on YouTube or something. But it's a lot of work. Maybe over the next year or so, after I settle into all the stuff that I'm doing right now, I'll be able to do that. So, because then that way, if I put everything on YouTube, then I don't have to teach all the time, right? I don't have to do tutorials. I can just say, hey, go watch the link to all the YouTube videos, or you can put the link in like the mega file or something. Everybody can watch the YouTube videos, and you know, saves me a lot of time. I don't have to do these tutorials anymore. So, not to say I don't want to do these tutorials. I think they're useful. It's just not. It's just not. I mean, it's hard to manage all the time. Cries in engineer. Cries in Spanish. That's a good one. I haven't seen that meme before at the new meme. What else do we want to talk about, if anything? The thing is, he usually does transmission lines before the midterm and sometimes puts them on the midterm. And so I usually spend some time talking about transmission lines. And so the years that I do these tutorials online, I feel like I have less material because there's only so much material that we have access to that is unique to his style of teaching or writing tests. So I don't. I it's not. I basically just run out of material because there's only so much that he does. So I guess as the years go by, I'm getting more material, but a lot of it's just the same crap over and over again. So I don't know. I don't know what to do today. I was hoping somebody would have a suggestion because there's not much on waveguides. If he decides to throw some crazy curveball for waveguides, it'll be bad for you guys, but it'll be a good indication of what to expect going forward. For me, at least, not for you guys. For you guys, it sucks. Solve more midterm questions, but like which one? I feel like I've done all of them. Like I feel like I've solved all of the midterm questions that were worth solving. Have I solved? Let's go back. Let's take a trip down memory lane. So we talked about some crap here. Fuck COV 538, worst course ever. Have I told you the story of what I learned in that course? Like the entirety of my knowledge. Have I ever been able to express that to you of what I understand, what I learned in that course? Okay, here's what I learned in that course. I learned that I don't know who's teaching that course, but when I took the course, there were two guys teaching it. There was Lev and Vadim. So there was Lev Kur, I can't remember his last name. It starts with a K, but I know Vadim was Vadim Gurkov. Those are the two guys teaching it. I had Lev. He's like an older Russian guy. Really funny, really nice guy. One of my favorite people. He's a nice guy. He's he's a fun guy. Um, he's he's older. He has a Russian accent. He has this very funny old people Russian kind of humor about stuff. He's interesting, right? So he's a great person. He spends a lot of time talking about stories, and he tells a lot of industry type stuff and funny stories about this and that. So I learned very little in that course, but the thing I think about when I the thing I think about when I think about that course and what I learned in that course was that Lev used to have a colleague. I think he worked in the same lab as him at Ryerson when this is back in like the late 80s, I think early 90s or something like that, when he first started. And he used to have a colleague who used to live in St. Catharines, and he used to have a plane, like one of those single engine planes. And that guy used to live in St. Catharines because it was much cheaper to live in St. Catharines, obviously, compared to Toronto. And he used to have a plane on a farm with a runway, and he used to basically fly his plane every day from St. Catharines across Lake Ontario, and he used to land at Billy Bishop Airport, and then he used to have a bicycle at Billy Bishop Airport that used to be locked there to the racks, and he used to ride that bike from Billy Bishop to Ryerson, teach, finish his day at Ryerson, take the bike back, go back down to Billy Bishop, and then fly his plane across Lake Ontario back to his home in St. Catharines. That is the entirety of my knowledge of COE 538 in a single story. That's what I learned in that course. So that tells you I didn't learn a whole lot. Oh, I found a question for us to do. We can do this question because we haven't done it before. But I can't find where it starts. Wait, what the hell? That's at. Am I like tripping? I'm like tripping hard. No, I'm not. What the hell did I do? We did this one. This is fall 2016. We did that one yesterday. Then we have this one. Starts there. A. That's B. That's C. D. B. A. Oh, there it is. Fuck. Just had the hardest trip out ever. Couldn't find the page. Let's do another transverse electromagnetic wave, because we haven't done enough already. And this one is like part A to part A to R. We're running the alphabet today. And I think this will be like the only problem I solve, because it's probably going to take about an hour, and I don't want to go on too long after that, because I'm sure I'll be done by then. And I don't mean done the problem, I mean like done, whatever energy I have left will be completely gone. So let's do a problem from fall 2015, I think. I feel like this is fall 2015 because that's what I've written. And I don't remember doing it before. I don't think we've done this problem, so I don't know. So this is question 3. The longest I've seen is part A to S. And also, just to comment on your thing, like, 'cause I just saw that and I forgot to comment on it. Like, you've memorized past midterms and got a 90. I memorized past midterms and got an A plus, and midterms and finals and got an A plus in that course. And I learned I'm not kidding. Like, I'm not saying this to just like crack jokes. That's literally the only thing I remember from that course. I don't remember anything else. Didn't learn anything else. I learned that this assembly language was stupid and low level and useful, but something I didn't want to have to deal with, so I wasn't, and that was the end of it. I remember my TA was not particularly helpful. He used to sit there and just talk to students and then walk around and just show us the solutions manual or answer sheet or whatever. But um, yeah, that's what I learned. But somehow I got an A plus, which further adds to my imposter syndrome that I deal with here and there, where I feel like I'm just fluking stuff, because that was a fluke. That shouldn't have happened. But that was years ago in a course that I care very little about, so oh well. Gotta do what you gotta do. Plus free dielectric x greater than 0 with epsilon r not greater than is equals 9. So you have that. You have E S I is equal to 240 pi e to the minus j pi x ax. No, it's not ax, it's az. Can't be a. Stupid. Yeah, C and Java are fairly intuitive because they're higher level programming, right? Like, the lower level you get, the more fundamental you get, the less it starts to make sense, because you're like, who the fuck cares about this stuff? Not me. I know that. A is the phase constant. Well, why don't we start by drawing? Because drawing usually helps, and he usually wants you to draw. I don't know what a good detailed sketch is by his standard, and I don't know how the hell I'm doing this or what I'm doing, to be honest. And I also don't know why I don't just use the line tool for all this stuff, because that would be of use. We can just do this, and that's your boundary. Wow, what an idea. So you have 1, this is air, and this is dielectric. So this is mu naught epsilon naught eta naught. This is mu naught 9. This is 9 naught 4. 9 epsilon naught, and then eta. Some eta. I don't know what that is. Then you have some incident wave. You have some reflected wave. I don't remember how, or if does he want you guys to draw the little circle with the dot in the middle and then show the magnetic field as well? I don't know. If he does, do that. If he doesn't, still, you could do that if you want to, but nobody's gonna care if you do it. So that is EST, and this is x equals 0. And I guess you can't technically draw what the amplitude should look like for the H until you see what the actual H field is. So. Oops. Part A is the phase constant in air. So I hope that everybody now knows that ESI can be written as ES or E naught I in general, e to the minus j beta x in this case. If you do this, you will see that compared with field in or the field that's given, you have beta 1 is equal to pi, and the units are radians per meter. If you missed his notation, how many marks are you gonna miss? I don't know. It depends on his mood. It depends on if he's grumpy and tired, and I don't know. It depends. I've seen people lose anywhere up to from like maybe 5 to 15% in some cases. I don't know what his rule is, but there's a maximum number of marks that he docks for things like that, from what I remember, unless he's gotten mean over the years. So the phase constant in the dielectric. What's the phase constant in the dielectric? The phase constant in the dielectric, we keep in mind that beta 1 is equal to omega mu 1 epsilon 1, and beta 2 is equal to omega mu 2 epsilon 2 epsilon 2. So if I do this, I see that I see beta 1 divided by beta 2 equals mu 1 mu 2 1, sorry, over mu 2 epsilon 2 under root. You see that the two mu's will cancel, and that becomes 1 over 9 under the root. So this is 1 over 9. That means beta 1 equals 3 beta 2. No. 1/3 beta 2, and so beta 2 is equal to 3 pi radians per meter. Okay. Part C, fuck, we have a long way to go, don't we? Wait, what? Beta 2 over beta 1? I did 1 over 2. It doesn't matter which one you do. You can take it whichever way you want. You can do 2 over 1 and then multiply it directly. In my case, I have to do one step further to rearrange, which is hardly a step. So you want to find, fuck writing the whole thing, I'm trying to write HSI. Find HSI. HSI can be found using the following equation: AP cross ESI divided by eta. In this case is eta naught. So AP, in this case, the direction of propagation is what? This, that we learned yesterday, is positive x, right? So if that's positive x propagation, this is AX cross 240 pi over 120, that looks weird, over 120 pi, because that's eta naught, because this is in air, e to the minus j pi x az. So we end up with the magnetic field intensity of the incident wave is minus 2 e to the minus j pi x AY. Amps per meter. This is HSI. It's a very long vector sign. There we go. That's beautiful. That's part C. Part D is eta 2. Well, I'm not going to do that because in some cases it's fine, in some cases it's not. So intrinsic, I think he calls it characteristic impedance more often than he does intrinsic impedance. Let's call it characteristic impedance of a dielectric. I don't know why I'm writing on a slant, but oh well. I think it's because my tablet's on a slant a little bit. Okay, better. Eta 2. That first one I made was so nice. What the fuck's happening now? There we go. Eta 2 is mu 2 over epsilon 2. So that is mu naught over epsilon naught times 1 over 9. So eta 2 is 120 pi over 3. So eta 2 is 40 pi. 40 pi ohms. So this is the same old stuff. I hope that in all these questions and all the stuff that we've done, I really sincerely hope that you guys all do well on this question at least, if not any of the other ones, because they might be new or something, but we've done this question so many times, and I really hope people are practicing it, because there's more to it than just watching me do the whole thing, because you're just watching and you're not doing, and on the test you actually have to do stuff. You can't just watch, unfortunately. Well, you can watch, because if you don't know what the fuck you're doing, then you're looking around like, oh, what do I do? How do I answer this question? And then you're watching other people answer the question, because you don't want to leave, because, you know, everybody's watching, and then everyone's going to think either A, you're really smart, or B, you're an idiot because you finished in 10 minutes. So I guess you can, you know, take a chance. This is 80 pi divided by, no, it's minus, well, let's do it this way. Let's write things out. 40 pi minus 120 pi divided by 40 pi plus 120 pi. Reflection coefficient then is minus 0.5. Oh my god, that's so good. That's one of the like the funniest things I've ever heard. Oh my god. That's definitely the highlight of the week. Maybe even the month, and I dare say the semester so far. I guess you can tell I've had a very shitty semester so far. Or that's just that great. That was great. Wow. Okay. Transmission coefficient. Tau is equal to 1 plus gamma. This is 0.5. Oh my god, that was so good. That is so good. part. Part G. Let's do it. Let's find ESR. And the reason I'm writing some of them and I'm not writing the other ones out because I would expect that you know what the which quantity the frequency domain reflected field is, the reflected electric field is. But when I write something like transmission coefficient, some people might not remember which variable that is. So for me to write gamma directly doesn't like show you the correlation between gamma and whatever explicitly. So I'm writing the ones out that are not as obvious because it kind of helps you think about things a little better, I think. So ESR, can't write in green anymore. ESR is equal to gamma times ESI. So this is, I'm writing really nice today. I think I figured out, I got this tablet figured out now. Minus 0.5 minus 0.5 times 240 pi e to the positive j pi x a z. And so ESR is equal to minus 120 pi e to the positive j pi x a z. And notice this is now positive. It's not negative. It's positive because it's propagating in the reverse direction or opposite direction, or whatever you want to call it. I is the total E in air. So the total electric field in air is equals ESR. One thing I should, I mean, all jokes aside, one thing I should warn you guys about is he said that he was leaving it up to you guys to solve the units. In some cases like that, I've even seen him say something like that and then do that thing because he was so ambiguous about it himself and told you to figure it out on your own. And then he just keeps, like, it's like a vicious cycle of never getting the answer and him just docking marks because you don't know the answer because there probably is no answer. So, you've been warned. Or H? Is it H? Whoa, whoa. I labeled something wrong. What the hell? E, F, G was the frequency domain. H. Oh crap! I completely missed it. I was writing the wrong. The wrong part. That is part I, but I looked over part H because apparently part H doesn't matter. So let's do this. Let's do that. Let's put H here. And we are looking for HSR. So HSR is equal to AP cross ESR over eta naught. I will add here, we can't use gamma because it is defined in terms of E, not H. So AP is now minus AX cross minus 120 pi e to the positive j pi x a z divided by 120 pi, and HSR is minus e to the minus j pi x ay. Getting close to the end now. My neighbor's car is so annoying. I don't know if you can hear that. Maybe you can, maybe you can't. I don't know how the filtering is on the mic. But apparently there's a guys that live in the basement of my neighbor's house, and he's like, he has a BMW. It's like a 3 Series BMW, and he it's like in really bad shape. But his thing is that he has a BMW, so he's kind of like proud about that. But when you look at it, it's in like the worst condition ever. So it makes these very strange noises when he starts it up, and he just started it up. So yeah, making a lot of noise right now. Anyhow, ES, the total ES, is 120 pi times 2e to the minus j pi x minus e to the j pi x a z. I just, something came in mind right now, and I don't know if he'll ask this question, but it's something that he might ask, and if he does ask it, you'll be ready for it, I guess. Well, can we even do that? No, never mind. I don't want to mention that right now. That's only applicable to transmission lines. Sorry about that. Well, is it? No, it's not. Okay, I'll talk about that in a second. Why is it e to the minus j pi for the reflected mic? Oh, that's wrong. That's a mistake. Sorry. Thanks. The thing I wanted to talk about when I was mentioning this is you might have a question. Let's say he might say express the electric field in terms of the incident wave and the reflection coefficient, right? So let's do that here for a second. This is a complete side note. And so this is let's express E as, not at, as ES and gamma, because he's asked this before in like a different context of a similar type of question, I think, somewhere. But to do that, basically we say ES is equal to ESI plus ESR, and you remember that if I have something like this, E naught I e to the minus, it's not a vector, dude, e to the minus j, let's say it's beta y, let's take the same thing, ax, plus e r, e naught r e to the positive j beta x. Let's say the whole thing is an az again. So the objective here is to express it in terms of ESR and reflection coefficient. So to do that, you would have to factor out E naught, you would have to e to the minus j beta x plus, this is not a vector again, plus you would have E naught r over E naught I, right? E to the j beta x az, and this is E naught, let's say I. Let's go ahead and factor out this this term as well, so it's entirely in terms of the incident wave, and so this becomes 1 plus E naught r over E naught I e to the minus e to the j2 beta x a z, right? So now what you can do is this term here is actually gamma. This is the reflection coefficient. This is gamma. And this whole term is the phase of gamma, right? So then what you can do is you can express this whole thing. And that was okay, I didn't want to undo that. You can express this whole field in terms of the incident wave and gamma, right? So this is E naught I, e to the minus j, e to the minus j beta x, 1 plus gamma, let's say gamma angle phi gamma az. So I don't know if you'll be asked this, but if you are asked this, then this is how you do it. I don't know why this just popped in my head for some reason. Maybe I'm picking up on some signals from Ali Hussein's planning the midterm or something, like interfering with his brainwaves. Or maybe he's sitting at the CN tower and he's like radiating these waves somehow. After I comes J. And part J asks for total HS. So HS is equal to the reflected plus the incident. So just straight up, I guess you can throw things together. Minus 2e to the minus j pi x minus e to the j pi x in the ay direction, and so that hs, the total, is equal to minus 2a to the minus j pi x plus e to the j pi x ay. Cool. Part J, then we have part K, we're almost there. J, K, well, we're actually not that close, we still have a fair bit to go. Oh well. Part K is the frequency domain electric field in dielectric. So we want to find transmitted wave. I guess his brain has some problems. He needs some protection. Yeah, well, maybe we can make him a tinfoil hat. And then give him the tinfoil hat. Or aluminum foil, because aluminum's probably a better metal to block EM waves than tin. But so let's get him an aluminum foil hat. And then make him wear it. And then we can watch him wear an aluminum foil hat and teach us electromagnetics. That would be fun. I wouldn't be able to take him seriously. I wouldn't be able to learn with a really old guy with a beard wearing a tinfoil hat. I wouldn't be able to take him seriously. I don't know, that's just me maybe. I totally can too. In my mind, I feel like it's an aluminum foil hat that is somewhat like a Viking looking hat. So I imagine it to look something like so if that's that part, then he would have like No, it would be pointier a little bit. So it'd be a little bit like this, and then it would look something like this. And I imagine because it's tinfoil, it'll have like all these like, it'll be all like crinkly and stuff. But I imagine him coming in like one of these, and then like face, and then like the beard. He would be like a fucking Viking. Oh my god. That would be so cool. You have a Viking teaching you electromagnetic theory. Wow. Wow. Okay. ESI is EST. What is this? 0.5 times 240 pi e to the minus j. I mean, again, notice here this is 3 pi x az, not x. Az. This is something to note because this is dielectric. Oh, let's put it in that. Dielectric. Electric. Oh wow, that's a good one. I should probably get rid of that. Why is it still there? Actually, no, we shouldn't get rid of it. We shouldn't get rid of it. We should just take it and then move it somewhere over here. Okay. Oh, what the hell? It's only that part of the hut. Okay, let's try this then. Okay. Go away. Not now. We'll deal with you later. Sorry. Getting sidetracked here. Priorities. Okay. Part L is HST. I should say transmitted electric field. I shouldn't say transmitted wave. Electric field. So HST, again, you can't define this in terms of the transmission coefficient. It has to be in terms of the electric field. So you have to say AP cross EST over eta 2. Now keep in mind this is eta 2, not eta 1. So you would have calculated that in the previous part. So AP is AX cross 120 pi over, it was 40, right? 40 pi e to the minus j 3 pi x az. So x cross z should give you minus ay. So you get HST is equal to minus 3 e to the minus j 3 pi x a y amps per meter. Okay. Part L. Part M. We haven't seen a lot of, well, we haven't seen this question at all. So this is, I guess it's a good thing that we did this. So, what is this question? This is part L, this is part M. So we want the maximum magnitude of the total electric field and the closest location of the maximum. So what we're doing is the field, obviously the incident and the reflected field create a standing wave pattern, right? And if you remember, we mentioned that that standing wave pattern would look something like this. You would have some boundary and you would have some wave, let's say something like this, which is a terribly drawn wave. and then you would have something like this, and they would interfere and create a standing wave pattern, right? But that was terribly done. I apologize for that. But you'll remember that these points were the points of interest, right? And if you remember, we said max at lambda over 2 and lambda over 2, or just to say lambda over 2, and then it's a minimum. Well, I feel like if I write it that way, somebody's going to interpret that as the wrong thing, so let's say n lambda over 2, and then it's a minimum at it's not lambda over 2, it's lambda over 4. So this was at even multiples of lambda, or is it even or odd? So it's 1, 3, no, 0, 2 is minimum. So it's 2n, so it's lambda over 2 for minimums. So this is n lambda, or we can just call it lambda over 2. N lambda over 2. N lambda over 2. Because it's at, no, yeah, n lambda over 2, because it's every 0 to pi, or 0 to pi, which is, fuck, what am I saying? It's 0 to pi, which is half a wavelength, and every integer multiple, whereas the maximum occurs at every, no, it's not n, it's odd multiples. That's what it was, it's even and odd multiples. 2n plus 1 lambda over 4. That was wrong. So it's every odd multiple. So the 1, 3, 5, 7, 9 are where the maximums occur and the minimums occur there. Oh, that was hard. So the maximums occur here and the minimums occur there. So then how do we find the magnitude of the electric field there? We plug that number into the electric field and we solve what the electric field magnitude would be. So we have E S, let's say, is equal to 120 pi 2e to the minus j pi x minus e to the j pi x a z. Okay, but what we need to do is we need to find lambda over 2 because we're going to need to plug a value in for x, right? And we know, or lambda, not lambda over 2. So then we know that lambda is equal to 2 pi over beta. I hope we know that. And lambda is 2 pi over beta, so that means this is 2 pi over pi, if I'm not mistaken. Lambda is pi, indeed, so this is 2. Lambda is 2. Okay, so then the maximum we say occurs at 2 n plus 1 lambda. That means the closest maximum will be at 0, n equals 0, which is going to be lambda over 4, right? So then we can take this one step further and say lambda over 4 is 2 over 4 is 0.5. Meters, because units are important, and if we call this point here x equals 0, then everything here is negative, right? So this, then maybe we can write these points out because we know what they are now. So this is lambda over 4 is 0.5, and then this would obviously be double that, so this is 1 meter. But the location itself has to be a negative number is the thing you have to understand here, because these are all negative numbers. So that distance is 0.5, but that location is x equals minus 0.5, right? So this is 120 pi times 2e to the minus j pi times minus 0.5 minus e to the j pi minus 0.5 a z. But now we want the magnitude of the magnetic or the electric field, right? So if we want the magnitude, then if I want the magnitude, then I take the magnitude of this thing. So the magnitude of the unit vector is 1. And you have this thing will give you 120 pi. What do I want to do there? Let's do this. E to the j pi over 2 minus e to the minus j pi over 2. Now, what's e to the j pi over 2 and e to the minus j? E to the j pi over 2 is cos pi over 2 plus j sine pi over 2. Cos of pi over 2 is 0, sine of pi over 2 is 1, this equals j. E to the j minus j pi over 2. That negative sign is too close. Minus j pi over 2 is cos of minus pi over 2 plus j sine minus pi over 2. This is minus j. So what we can do now is we can substitute this into the expression over here. That 120 shouldn't be in there. It should be on the outside. This should say 120 pi, right? So then you have, well, the magnitude of, no, that was fine. So silly. Sorry about that. There should be a bracket here. That's what I was missing. I knew something was missing. So what you get is that evaluates to magnitude of 120 pi. This first thing, there should be a 2 here. This first thing becomes 2 times j, and this is minus j magnitude. And so this is what is the magnitude of 120 pi times 3j. The magnitude of 3j is 3, the magnitude of 120 pi is 120 pi, so this is 360 pi volts per meter. And we can say this is ES magnitude. Occurs at x equals 0.5 meters minus 0.5 meters. Is max being odd and min being even a constant? Yes. So long as you assume your waves look like this, which in the standing wave pattern we assume they do, this is true. This is true because of the way that the wave interacts, right? Like this is a half a wavelength, this is a quarter wavelength. That's what we imagine them to be. If the reflected wave has a phase, which it doesn't in any of these questions that I've seen at least, if it has a phase, then that maximum minimum condition is not necessarily true. There's a more general expression for that, which would basically be looking at this expression and then finding out when pi x equals a minimum, and then you can go about that. But again, if it's not in phase, then it's a case by case thing. So part N is SWR in air. So the SWR in air, S equals 1 plus magnitude of gamma over 1 minus the magnitude of gamma, and that's 1 plus 0.5 divided by 1 minus 0.5, so S is equal to 3 in this case. Part N, this is part O. SWR in dielectric, S equals 1. No reflection in dielectric. Part P is time average Poynting vector of incident wave. So PAVI is equal to 1/2 real of ESI cross HSI conjugate, and that is 1/2 real 240 pi e to the minus j pi x ax az. I was writing x. Why do I keep writing x? It can't even be possible. Az cross minus 2e to the positive j pi x ay. One thing we know is that this should propagate in ax because that's what power does. And this is a power density. If you evaluate this 240 pi times 2 divided by 2 ends up being 240 pi. And z across minus ay is ax. The units are watts per meter squared. This is PAVEI. Part P, Q, we're almost done. This is repeat P for the reflected wave. AV, no, not reflected. I want to say transmitted. Why the hell did I write reflected? So dumb. I think I may have seen an R somewhere and I was like, oh, of course. That means reflected. PAVET is equal to 1/2 real EST cross HST conjugate. This is 1/2 real 120 pi e to the minus j 3 pi x az cross minus 3e to the j 3 pi x ay. And if you solve that, I'm not going to go through all the steps because it's kind of silly. I hope you can solve that. If you solve that, you get 180 pi ax watts per meter squared. Okay. Now the last question. Okay. Percent of incident power that is reflected. Okay, how do we do this? How do we do this? There's a couple of ways to do this. One way to do this is to remember some equation that is written somewhere in the textbook that says PR over PI equals the magnitude of gamma squared. and that is minus 1/2 squared, which is 0.25. This is from textbook. Now you may be wondering, what happens if I've never seen that equation before? Because I've never seen the textbook before. Because what the hell is a textbook? Or we know that the total power transmitted has to be conserved. Our energy has to be conserved. So we say energy has to be conserved. So what does that mean? That means PAVT plus PAV, not T. I wanted to say, well, I could say T, but then I wouldn't put an equal sign here. Let's keep T there. Is equal to the incident minus the reflected. I hope everybody can agree with that. So if you take it this way, you can literally take the magnitudes and then understand that this is the amount that's transmitted and then divide that by the incident, right? So the only issue we have in this case is you don't have a reflected power. You have the incident and you have the transmitted. So if the whole thing must be equal, then you can find what this reflected is. And so that's the point of me writing this was, well, maybe I probably should have wrote the other way. So then I can say that PEVR is equal to PAV T I. Is it I? What did I write? PAV. Wait, what? Why am I losing? What did I do here? What did I do there? What is that? That's what I was looking at. That's confused the shit out of me. What is that? What is that? What was that? Anyhow. Ends up giving you PAVI minus PAVT. So that means whatever the reflected has to be whatever's incident minus whatever's transmitted. So if you think about that in this case, they should probably all be magnitudes, let's say. Where the vectors, it's true for the vectors too, but if we want to take the magnitude then of this thing, that means that the magnitude is equal to 80 pi minus that 60 pi, right? So if that means the magnitude of the power is 60 pi, then the percentage that's reflected to what's incident would be PAV. So then you have percent reflected is equal to PAVR divided by PAVI. And again, like I do things this way because I don't like to memorize stuff. So I understand conservation of energy, so I say, hey, let's do it this way. So this should be 0.25. I hope. 6 times 4 is 24, and then you put zeros on the end of it, it's 240. So yeah, that's my way of doing that. And then, like I said, again, it's just so you could do things without memorizing them. But if you like to memorize, because I know some people like to memorize because they don't trust themselves to think on the spot, should they need to. So I give you the memorizing way to do things as well. Wow, that was a good question, wasn't it? How long did that take? That took quite some time. Any questions about that? Or anything questions about anything in general? No questions? That's cool. That means either I'm doing a very good job or nobody has any idea what the hell's going on. Words of wisdom. I have words and very little wisdom. Therefore, I imagine my words of wisdom are very scarce. So, if you want to know about something in specific, like you want me to comment on something, I most certainly can. But yeah, you could say that it's 1 minus the reflected minus. Wait, no. 1 minus PAV R over that's going to give you the opposite. Yes, 1 minus transmitted over incident will give you the exact same. Because that what you're suggesting is can also be extracted from this equation, because you can divide things out by PAVI here, for example, and then you'll get 1, and then you can rearrange things. But yeah, 1 minus that transmitted over incident is correct. So like I do things this way because, like, I mean, like, I'm not doing this because this is the best way. I'm doing it, this is the way that things flow in my head. If you do it in a single step equation, that's wonderful, but I don't like to give myself that much freedom, because then I start making very interesting equations sometimes that make absolutely no sense. And I don't mean interesting in a good way, I mean in a bad way. Can you explain what a crystal detector is? Something that detects crystals? Mm. No, I'm kidding. Um, as far as I know about crystal detectors, the crystal detectors themselves are fairly obsolete um, radio receivers, basically. And I say obsolete because they were used earlier on, but nowadays we have much better things to rely on than crystals, because we can make much better circuits in general. With improvements to manufacturing processes and technology in general. But it's basically, it was a receiver that would, because I don't know if you guys know about, you'll learn about this next semester if you take ELE 635, or if you've already taken a 635. You have to modulate and demodulate signals when they're transmitted, basically. So AM modulation, for example, is amplitude modulation, which is literally why you have AM radio. And then FM is called frequency modulation, so you basically, that's why you have FM radio. So if FM allows for much tighter or much more precise bandwidths and specific frequencies and such that you can have more channels in a narrower range. Whereas AM does not allow for that, just based on the technique and the mathematical formulation of the thing itself. So yeah. In any case, these crystal detectors would be used to demodulate signals that were modulated and then transmitted. So nowadays you don't really use them, and I don't know if they mention them in this course, but that's what a crystal detector is. Were the notes for the tutorial? The tutorial notes are not posted. I will post them after this because they're on my laptop. I didn't get to do that. So, is there any purpose to the labs? I imagine there is, but for me, it's very hard to see it. At least in the current thing, there's there is practical use if explained properly, but I don't think they're explained properly, and there's a big disconnect between the labs because they kind of just stand alone. They don't do anything. They just fill a void. In my opinion, tutorials would be more useful for this course, and field theory should have labs. It should be the other way around because field theory tutorials are not as useful. Labs would be much more useful, and you can do some very interesting experiments with fields and static stuff. But you know, I suppose a lot of things could be improved. Yeah, the labs do not coincide with theory at all. They're kind of just this thing, this bastard child of the course that's been tossed aside and told to exist on its own. But hey, I guess that happens sometimes. How is the rest of the semester going? Are the other courses going well? Yeah, I have an exam on Tuesday as well that I probably should be studying for, but this is kind of like studying because the exam's on ELE 5315 40 504 404 and 401. So yeah, it's been a fun time. Decided to take a comp course. Consider Breeze. Which course is that you took? The exam that I'm doing is it's the PhD candidacy exam. Maybe I'll just show you guys the thing itself. So this that's 2007. Well, actually, it's the same. This is old. It's this thing. So this list has changed over time, but it's basically like so. Basically, I pick a list. I pick some courses from like a list like this. The courses have been changed to add. They've included some of the second year courses as well. So I took. So the courses that I picked were ELE 404, 504, 401, and 531. Simply because 531, 401, I do tutorials for. 404 I taught last year twice and have done tutorials for the last 3 years. And then 504 is a relatively simple course that's all about op amps and what to do with them. And so I've been studying that for the last 4 weeks or so. And I have the exam on Tuesday morning. So it's a 3-hour exam, so it's 45 minutes per course question thing. And should be fun. So I mean, I wasn't planning on writing it initially. I was planning on doing it next year because you have 20 months from the beginning of from the beginning of when you enroll to the into the program. So I basically have 20 months from September from this, like last month, so I have 19 more months to do it. I was planning on doing it next year, but then my supervisor asked me why I wouldn't do it this year because he wants me to move things along. Like he has a lot of plans for what we're doing during my PhD. So I mean, it's there's quite a bit of work to be done, to say the least. And so he wants me to move along with things as quickly as I can. So he's asked me to. So he's suggested I should do it. And he laughed and said, "You TA and teach basically all the courses. What are you worried about?" And I was like, "You're right. Let's do it." So I went into the meeting talking to him, and he was like, "I don't know if I want to do it." And then I left, and I was like, I thought about it for 5-10 minutes, and I printed the form out, had him sign it, and then I submit it. And so it's Tuesday morning, 9 o'clock. It's 4 courses in 1 exam, but I mean the courses are very fundamental, and at the same time, you have to understand. Like I've been teaching the stuff for a long time. I took the stuff myself a long time. I'm fairly familiar with most of the things off the top of my head. I really enjoyed these courses. They are my favorite courses in the whole program. Those 4 were probably my favorite. And then if I had to say top, my most favorite one I think is field theory. Although I don't know, but they're definitely among my favorite courses. So it doesn't feel like it's going to be too difficult. So I'll be fine. How hard is it to get into a master's program? There are different types of master's programs. So the master's program I did was a research based master's program. but you can have master's programs that are more course based. For example, we have two programs in our department. We have the Master of Applied Science, we have the Master of Engineering. So in the Master of Engineering, it's basically like doing another year. So if anybody wants to do a master's but doesn't want to spend too much time on it and is afraid that they might not be good enough to do research but still wants a master's, apply to the Master of Engineering. It's like you have two options to do it. You can either do 10 courses and you're done, or you do 8 courses plus like a research design project, basically like another capstone, but a little more advanced because you would know a little more stuff. But it's more or less the exact same. It's basically doing another year of undergrad because you already do 4 or 5 courses a semester, and you can add the fact that you have a master's to your name. You become a little more employable if you go with the industry and decide to take that route, which most people do actually. So you'll end up with a little more money than the next guy if that's important to you. Masters of Engineering is just a bunch of courses. On the other hand, if you have to do a Master of Applied Science, you do what I did. I took 5 courses, and then I did a research thesis. Now, the research thesis is usually something that is, I won't say novel, so it's not brand new, but it can be. It can be a new aspect of something, in which case you would end up writing a paper or something after you're done. But it's usually something cutting edge. You do a research thesis, you review the literature, what's going on in the world, you contribute some theory or some application or something, and then you write a thesis about it. 80 to 100 pages, I would say. So it's a different type of thing than you've ever done, I guess, is the simplest way to put it. Like, research is very open-ended. It's a very non-linear path in that you can be working at something every day of the week and still be making no progress. You can be working for 10 minutes one day and basically solve all of your problems. So it's very non-linear. It ebbs and flows, and it's very interesting to me, at least, which is why I'm doing it. But yeah, both types of things are viable. If you want to be doing research and you're working with Vadim, first of all, it's very good that you're working with Vadim. The thing that I've found, and the thing that's led to most of the success that I've had, or achievements, I should say, because success is relative, but the achievements that I've had so far have been a result mainly of a relationship that I built with a professor that benefited me in multiple different ways, time and time again. Because I met Yazdani when I was in my second year, so he taught me ELE 404. And earlier on, I kind of really started to, like, I found that I liked his character, he liked mine. We enjoyed having conversations. It was mainly just me going to him for a lot of help and asking a lot of questions. But when I got into the masters, I was basically guaranteed a spot because he really wanted to work with me. When I was in the masters, I had a lot of benefits because he was willing to, recommend me for certain things or trying to work in my best interest. But that happened from developing a relationship. So if you realize you want to do grad school or you want to do research or something, and you realize that's the kind of path you feel you would be better inclined to go down, then I would suggest you stay in touch with him and get develop a good relationship with him, where if you wanted to and you wanted to use him for that type of thing, you can consider working with him. It just makes things much more comfortable, in my opinion. Like, when I talk to Yazdani about stuff, I don't it doesn't feel like he's a prof or he's a supervisor and I'm his student. It kind of just feels like it's another guy that I know. He's a friend, and we just chill and we shoot the shit about stuff for quite some time, sometimes actually several hours at a time, sometimes. So it's a lot of fun. It makes things enjoyable, and it gives you the benefit of that as well. But then, there's always the option of going somewhere else. So the fact that you're doing research, and you're enjoying it, that might be something to consider, I guess, a little more seriously as a result. It's not difficult to get into a master's program, especially if you know the person who's who you want to work with. So maybe I should post those other notes now too. In the meantime, I'm guessing we're basically done here. So if anyone's sticking around just because they're expecting more work to be done, I'm pretty sure it's not going to happen. Oh no. What time is it? Holy crap, it's almost 11. I should go to sleep. That's what I should do. Probably after I post this. That makes sense. It makes there's value in learning different things, but at the end of the day, you want to do obviously whatever interests you and excites you. So if that's not the thing you're doing now, then you should aim to do that in the future. That's what I would suggest, at least. So why don't we go ahead and post this? There they are. Okay, cool. What are posted? Is anybody applying for internships or gotten any internship news? I know one. I talked to somebody that yesterday. They were getting an interview with AMD, so that was interesting. Yeah, still in the process, I guess. AMD jobs are pretty are the best ones from what I've heard, at least. The I don't know about Synopsys if they're good, but I know that AMD, for the most part, I've heard a couple of negative reviews about them, but for the most part, I've heard nothing but good things about them. It can be a really rewarding job. I have some friends that work in AMD as well that graduated around the time I did. In fact, I have one really good friend who's been working there for 3 years now doing layout, and he started off different at a different place, but then I got him a job through some other guy because I knew another guy who graduated with me. My friend, that the one who I know doing layout, he started there earlier. No, he finished later. I was earlier. I don't know why I said he started there earlier. He finished his degree after me because he got an internship, but I didn't, which he used to always make fun of because he got an internship and I didn't. But then when I used to laugh at him that my GPA is higher than yours, so fuck you. But anyhow, he got a job at AMD and he works there. He's been working there for about 3 years. So if anybody gets a job or an interview in any of the layout positions, if you get an interview there, send me a message or an email or something, and I'll see if I can get I can recommend you and be like, yeah, you know what? And I'll only recommend you if you're actually worth recommending. I'm not gonna put myself out like that and say, yeah, I recommend this guy, and you turn out to be a piece of shit. Not that I would tell you you're a piece of shit. I might just not recommend you. So, if you got an AMD layout related interview, send me a message and I'll see if I can do something for you. Celestica, I know some people really enjoyed Celestica. Some of my brother's friends worked there. They were in mechanical. I know some electricals that worked there as well. So it can be a nice one, I think. I think I'm gonna call it a day. 11's late enough, I think, for me. Considering how I've been up since like 5. Had a busy ass day today too. So, I'll post these notes online, as always, right now. And I will probably head off now because it's 11 and we started at 9. And I guess I gave you guys 2 hours, which I usually do. But the last hour, or I'd say about an hour of the total thing was not... about an hour was probably not overly productive because there was a lot of banter in the middle. But anyhow, I may or may not do a tutorial sometime during the week, maybe like Wednesday evening. If you have like any last minute questions or any questions, I won't like present any problems, but if you have specific problems that you want me to address, I can look at those. Overall, I mean, this is what it is. This is all that. This is whatever's in the course. I mean, it doesn't get any more crazy than this, unless he brings some really crazy waveguide stuff out. I don't know what he's gonna do with the waveguide stuff, to be honest, because I've never seen waveguides on the midterm because he's never done it that way. Still, it'll be more or less the kind of stuff I did in my notes. Point of the story, I will do another tutorial maybe on Wednesday, and I'll just sit here for a couple of hours and we can just talk and you can ask questions and I'll just literally just sit here and answer questions. I won't present any, but I will answer questions. And so, in the meantime, if you have questions, you can send me an email, send me a message or whatever, or comment in the Facebook group, wherever you feel most comfortable communicating. And if there's nothing else, which I don't think there is, I will see you guys later, and I hope you all have a good night.